Hello, I'm Xavier Degelis, Solution Architect for McKesson Specialty Health. I'm going to present today the final project presentation about Azure Container Registry. First, the problem statement. As the number of applications and systems grows organically, the need for normalized system deployment, the ability to scale on demand according to business needs, and the capacity to have a resilient architecture is driving towards containerization and orchestration. Azure Container Registry, ACR, is a standard-compliant, high-performance repository to store securely images for container deployments. ACR supports Docker, layered image format, and client tools for a seamless DevOps automation. It provides a full solution for container lifecycle with integration to Azure Container Instances, bare metal Docker containers, and services, aka Kubernetes. Our methodology consists of 4 steps. First, convert our reference stack from a granular RPM pool to a Docker image. Second, create a high-performance and secure ACR instance and deploy the image. Third, deploy from the registry and Azure Container Instance, which is a native Docker container. 4. Build a Kubernetes cluster, AKS, from the reference Docker image hosted in ACR. Our conclusion for this project is that the Azure solution, combining registry, native Docker containers, and orchestration via Kubernetes, achieves our 2 primary goals: system consistency and on-demand adaptive response to outages and business activity variances. We also want to present our reference architecture in this project, which demonstrates that the Azure Container Registry is a pivot for container services and orchestration. This project also emphasizes that system normalization and elasticity is achieved by containerization and microservices. First section, our development environment. Our platform consists of Oracle Linux 7 with UAK4 kernel, Docker Engine 17, Docker Compose, Azure CLI, kubectl for cluster management, and the XGForge internal yum repository. The Docker Engine is installed via an RPM package and yum install. The Docker volume is created as brtrfs and auto-mounted at bootup via Docker storage config. The systemd service is configured to auto-start. Then we validate via Docker info that is connecting to the daemon and returning the engine version number. The Docker image build process supports a YAML template for Docker Compose, which is really the docker-compose.yml file, and you have an example on the screen. All the system artifacts are stored in the .docker subfolder, the Docker file, the startup script, all the web configuration files, and the fastCGI configuration files as well. The Docker file is the most important file of the build process. It is used to configure the image content or the binaries installation from XGForge. It contains logic to install, upgrade all RPMs as necessary, verify binaries, copy custom daemon configurations, and init script. All the application code modules are located and presented below, mostly all the caching technology, memcache dashboards, PHP dashboards, and the health monitoring PHP script. We also developed for this project a build script, build.sh, developed to auto-generate the image and execute it. All the source code is on GitHub. The build script has 4 major steps. First, reset the Docker environment to remove containers and images. Second, download the latest base Oracle Linux 7 image for Docker Hub. Third, execute Docker Compose to build the layered image from XGForge RPM. And last, start a derived container and operate basic checks. The resulting Docker image is presented below and is validated via 3 commands: docker images to list all the registry locally, docker ps to see if the container is running, and docker stats to have running statistics on the container. The application validation also is tested to demonstrate the container health by accessing the web app URL. The Nginx status and PHP status is also displayed successfully. At that point, the local Docker container is fully operational. Now we can move on to the Azure Container Registry ACR configuration. First, the registry creation. Using Azure CLI, an ACR instance is created with a premium SKU that allows us to implement geo-replication and high throughput capacity for ACI and AKS. The name of the container registry is also displayed, as well as the FQDN of the registry login server. The next step is to authenticate against the registry from an automated process. Although a service principal method with Azure Active Directory integration is also available, enabling the registry admin offers a simpler method to authenticate container services from Docker client, from ACI, and from AKS to the registry by just entering the registry name as user ID and the admin access key as password. Below, you can see the Azure CLI commands to enable the admin and also to display the access key. We're also interested in geo-replicating the registry. ACR with premium SKU can be configured to replicate across multiple regions for data redundancy and speed of access to images. Using the Azure CLI, we are linking 2 regions, West US 2 and East US 2. The status initially is syncing, then becomes ready. And you can see here that the 2 regions are now perfectly in sync. After geo-replication is enabled, we are now ready to push Docker images to ACR. First, the image needs to be tagged with the login server name, and you have the Docker tag command below. The image is then pushed via Docker push to the Azure ACR repository. The name of the repository can be displayed, as well as the tag value, which demonstrates that the image is intact and uploaded successfully to ACR. Now that the registry is healthy with the image uploaded, we are now going to test the ACR registry from Azure container instances called also ACI. So first, how to do container deployment in ACI. We have now a lot of detail around the Azure CLI command, AZ container create. And as you can see, you need to pass the name of the container group, the name of the image pushed to ACR, how many CPU and memory you want to allocate, the admin credentials to log on to the registry. We also want to allocate a public access for external access on port 80. Please note that the port translation is not supported. That means that the port within the container needs to match the outside port of the container. Oddly, ACI is not available in East US 2, so we select East US as a region. The DNS name label is used to register the container associated with the public IP in DNS. And lastly, the command line is used to execute an init script as startup to launch in this order memcached, PHP FPM, and Nginx. Please note that memcached and PHP FPM are demonized, but Nginx is not, as the Docker container needs a foreground running process to stay up. The container validation step is performed via the Azure command AZ container list, and it returns the provisioning state succeeded. It also can be displayed in Portal as well via the container group object, and it shows also that the resource group is correctly created and that the container is running. The application, since the container is started, can be now validated to demonstrate that the ACI container is healthy and major components functional. The application will be accessed remotely via its URL. 4 sample tests are then performed to validate each service: Nginx, the PHP health check, the FPM daemon, and the memcache daemon. And you can see the dashboard where basically all services are displayed properly and show the correct status in ACI. So the container is up, the application is returning successfully all dashboard fragments. Since ACI was successfully deployed, we now want to test the Azure Container Services and AKS in relationship with the Azure Container Registry. And we are especially interested in Google Kubernetes cluster. First, we're going to create the cluster via CLI as a single node in region Central US for better performance, and we also want to target version 187 for stability. The command is detailed below with AZ AKS create. The provisioning state must be succeeded at the end. Then we need to merge locally the AKS cluster credentials. The command to do so is AZ AKS get credentials. Then we want to perform a basic health check to verify AKS cluster connectivity by executing the command line kubectl get nodes. This command will return a ready status of the agent pool, as you can see below. An important topic now of ACR credentials. Since a private registry is used, a secret, reg secret, needs to be created to hold the authorization token to ACR via the command kubectl create secret docker registry reg secret. This is extremely important so that Kubernetes can pull images from ACR, which is a private registry. The key requirements for a successful deployment in AKS is to store the reg secret value in the attribute image pool secrets in the YAML manifest k8s.yml, and this is mandatory to access a private Docker registry from Kubernetes. An Azure load balancer with availability set is used to front-end parts. The most important step for deployment is to build an application manifest. The manifest file k8s.yml defines Kubernetes objects. 3 important indications here. First, the image that we need to pull, and you see this is the ACR fully qualified login server name with the image name and the tag. Second, since it's a private registry, we need to make sure that the attribute image pool secrets points to the reg secret information stored previously. Third, we want to implement a load balancer on port 80. The Azure load balancer, which is a standard load balancer in Azure, will be used. Then the application can be deployed to the cluster via the command kubectl create. This command will instantiate and start the nodes and the pods. It will also start the Azure load balancer and provision the external IP address. The cluster node validation can now begin with the load balancer service via command kubectl get service. And you can see that the external IP is provisioned and the port 80 is active. Also, the cluster resources and status can be validated via command kubectl get pods. And as you can see below, the Nginx pod is successfully running and provisioned. The application scaling in AKS. To respond on demand to changing environment, we're increasing the number of application containers to 3. As you can see here as the screenshot, count 3. The command used to do so is AKS scale, and node count is 3. We then want to align the pods to have multiple replicates, 3 replicates, via the command kubectl scale replicates equal 3. And you can see that the result of that command is 3 pods being deployed to the cluster. Also of interest that the horizontal auto-scaling is supported with AKS with a trigger. That trigger is typically CPU utilization, but can be other parameters. This allows you to have true elasticity on the cluster. We then want to tune the load balancer provisioned. We want to verify that the load balancer is healthy in Portal, and we want to make sure that it includes, as a backend, the 3 Kubernetes VMs. A DNS name label is also associated with the load balancer, public IP, and the backend health probes are changed to HTTP GET. The application is then validated on AKS. The home page is displayed via the load balancer VIP. All members of the availability set are proven to be load balanced by accessing the health page with multiple browsers, and to make sure that the remote header and server header changes. That means that the VIP is load balanced across the backend. Azure Container Services AKS also includes very sophisticated container monitoring. Azure offers a container monitoring solution as part of OMS. The workspace ID and primary key are added to the manifest file, which is then used to create monitoring agent. The command to do so is kubectl create and then the daemon set YAML file. The container monitoring console is then accessible via Portal, and the AKS instrumentation portal is now fully configured with container events and logs, Kubernetes events and namespace inventory, container process, and CPU and memory performance. Thank you for your attention. This concludes our presentation.